Bussenger from Florida Tech and SpaceX. Wait, how can you be from both places? You do some part-time work at SpaceX?
I am full-time SpaceX.
Cool,
I do part-time work at FIT.
All right, so you know some guy named Mike Taylor?
I know some guy named Mike Taylor.
Yeah, he's my bud. Cool. All right. Next you got Joe's from SpaceX, the real rocket company, and he's going to talk about the FIT Pathfinder program and their 6 degrees of freedom static test stand. Don't forget, the vendors are waiting for you to check their wares, and there's still a few patches and t-shirts for sale at the front desk. And with that, I will leave you. All right, enjoy.
Good afternoon, everybody. As mentioned, I'm Joe Bussenger. I graduated from Florida Tech last year, 2013. I'm a full-time mission operations engineer at SpaceX. Today I'm going to talk about a few different things. I'm going to talk about some of the programs at FIT as they pertain to amateur rocketry, experimental rocketry, and some of the facilities that we utilize at FIT. Really quick, Florida Tech gaining more and more popular, not just in the area, but nationally and internationally. It was founded in 1958, very young university. It's about an hour south of here in Melbourne. The Florida Tech was essentially started up as Brevard Engineering College for engineers in the space program. So it has deep roots in rocketry, deep roots in aerospace, and a lot of that is evident today. So one of the unique centers that we have at FIT is the Center for Commercial Space Transportation, where we're able to utilize some of the funding, concepts, and just the interaction with commercial space program and commercial companies to further some research at our facilities and to utilize some of our facilities for the betterment of commercial aerospace. Again, as I mentioned, I'm Joe Bussenger, graduate with a BS in Aerospace Engineering. I've been involved with the Student Rocket Society at FIT. Essentially, that society, we actually will pay for members' kits, we'll pay for their hardware to get them certified with the NAR, with the hopes that they'll continue their interest in aerospace and rocketry and get more involved with some of the projects that we have, such as the thrust stand or some more advanced rocket projects. Currently, I'm a SpaceX mission operations engineer. I'm also involved with 2 companies I'm partnered with, one being a 3D printed technology company, and the other being a rocket engine company. So, again, I'm going to cover 3 different aspects of Florida Tech. I'm going to cover our testing capabilities, one of our launch programs, and a piece of hardware that we developed that kind of brings it all together. So first, one of the items that we're really proud of at FIT is our 6 degree of freedom thrust stand. Most thrust stands that we look at measure only axial thrust because that's what we're concerned about in rocketry. However, when you're designing and making your own motors, you're not going to make them perfect every time. And we developed this thrust stand to be able to examine any kind of off-axial thrust, any roll torque that the motor might actually produce, if there's nozzle issues, if we have some odd chamber resonance. So that's what the thrust stand was actually designed for. So it's able to measure not only the axial thrust, but also the thrust and the pitch, yaw, and roll. So we have 3 different stands. We have a horizontal test stand, which you can see imaged with an L930 motor on it. We also are developing right now, and it's completely fabricated. We're just looking to actually erect it as our vertical thrust stand, which will be capable of firing motors up to 10,000 pounds in thrust, and it'll be capable of firing hybrid motors and liquid engines. We also have a smaller vertical test stand that's good to fire engines up to about 10 pounds. So these would be smaller hybrid motors, the fun ones. So how do we do 6 degrees of freedom? Definitely not an easy task when it comes to trying to measure with a high accuracy. We use piezoelectric sensors, so we can actually measure at about 10,000 hertz, which is a lot of data when you're firing a motor for just 10 seconds. So we have 2 main sensor heads, the main one being in the aft, which the actual rocket will butt up to. That has 3 different force sensors in it, again, all piezoelectronic. It also has a roll torque sensor as well. So that mainly sees the brunt of the actual thrust from the motor. On the forward end, we have something that's called a steady rest. Basically, it's a triangular shape with 3 different single-axis piezoelectronic sensors. And what that does is they'll actually contact the motor on these ball transfers ball transfers and then put the force on the actual piezo. And from that, from the sensor head, the 3-axis sensor head at the aft end, and then the 3 sensors that we have on the forward end, we're able to actually determine the overall thrust vector. So just to show you, right now you're looking at the steady rest, and to show you that L930 motor firing. So that'd be an example of a quick test, and right there we captured about 11,000 data points. So we're collecting data at a very high refresh rate. So what I want to do is I want to introduce the Centurion program. The Centurion program at FIT was developed when there was a competition by Mark Carmack to launch a rocket to above 100,000 feet. Now, we started this about 3 years ago, and the program's really evolved because in the local area, there's a great deal of concern and interest to start raising our abilities to launch smaller, and I say smaller, rockets actually out of Cape Canaveral. Right? This would be on a range asset launch pad, and we'd be able to launch to 100,000 feet plus. So now the program's evolved from launching to 100,000 feet to the next vehicle in line launching to 300,000 feet. And that's where we're really starting to get into a launch schedule now where we're going to be testing these systems out. So that's the Centurion program. And now what I'm going to talk about is the hardware that we needed to get there. And I'm going to choose one piece of hardware, and that's our thrust vectoring system. So early on, when we were talking with the range of potentially launching a rocket to 100,000 feet, the first thing, obviously, out of the range's mouth is you need a flight termination system or trajectory control, you choose, or both. So we were actually able to talk them out of having a flight termination system on board. And if you've ever dealt with an Air Force range before, that's not easy. So we then convinced them that we want to bring you along into a design, fabrication, and a testing program to show you that our trajectory system is going to work and we don't need flight termination. So that's what we did, and that's where Vector Bravo, which in the military stands for 100% on target, evolved from. So this is actually our system. Is completely independent and it is closed loop once fired on the rocket. So this uses vanes that are actually put into the plume of the motor firing on these high-geared, titanium-geared servos that are actually able to pivot the vanes and direct the thrust. We're able to get pitch, yaw, and roll out of these vanes. Now, all 4 of the servos are then programmed to a flight computer and an Arduino. And there's already a pre-programmed flight path on the Arduino. So using 3 GPS that we have on the actual rocket, accelerometers, and a gyro, the rocket's able to determine where its flight path is in coordination with its nominal flight path with a certain envelope. So if it starts to deviate, it'll start to vector the rocket in a certain orientation. Originally, when we were going to fly out of the range as well, to avoid flight termination, we were actually going to fire at a 60-degree angle. And then once we got about a mile out towards the ocean, we were then able to go completely vertical. So that's what our nominal trajectory plan was going to be, and we were actually able to somehow talk the range out of that as well, and we were able to fly straight up. But that's what this system was designed to do, to be able to carry the rocket from 60-degree angle of attack to straight up 90 degrees to 100,000 feet plus. So there's several project requirements that we had. The first requirement was that we must be able to vector 5% of the total axial thrust. And we had to keep the system weight less than 10% of the actual launch vehicle weight. So we actually had to keep the system less than 30 pounds. The final weight signature on it was about 8 pounds. So we were well within that requirement. And for the system requirements, we also had to obviously develop this for use on potentially a few different rockets. So and what I mean by that is a few different size propulsion systems. Originally, we were going to fly on a hybrid, and then for ease of testing, we actually moved to a solid. But in order to do so, we had to develop different vanes and different shaped vanes configured for that actual motor's profile. And that essentially is based on the type of shock that's going to form at the nozzle, the type of shock that's going to form off of these vanes. And for a hybrid, it's a lot different than a solid. So we had to be able to make this system so that it had interchangeable parts, and we did. So we developed 3 different systems. We developed a practice prototype, which was just testing our machining ability. All this was machined by undergraduates, all designed by undergraduates. So our machining, I wouldn't say is 100% top-notch industry standard. So we had a practice prototype, where essentially we made everything out of aluminum, we put it together, we looked to see if we had any collision issues, which we did, so we're happy we did do a practice prototype. We were able to change that out pretty quickly and then move on to our test prototype. Our test prototype, the only difference is that we actually have a plate that makes it easier for the system to integrate to our thrust stand. And then we have the operational prototype, which would be carbon fiber. It would have the actual servos themselves would not have any cases on them. Essentially, we were just cutting down on the weight, but the overall system ConOps and the overall system integration is the same. So this is essentially what it looked like. And I mentioned the plate that was needed for testing. That's this bottom plate. And you'll see in a few later slides that the servos, how they actually fit into the rocket, they're actually hidden in nacelles. And off of these nacelles are the actual fins of the rocket. So the system has no aerodynamic signature on the actual vehicle itself. It's not like we would have a servo just sticking out into the open airstream. So here you can see that we're actually integrating it onto the thrust stand. We're going to, with our testing program, we're not only testing the thrust vectoring system, but we're also verifying complete control and performance of the actual thrust stand. Thrust stand has never been exercised with a motor this size. We were firing on an M750 motor. And the thrust stand was never exercised in all different axes to 10% of the thrust. So this was really us kind of stretching our legs on both the thrust stand while also getting the performance characteristics of the actual thrust vectoring system. So this is what it looked like when all was said and done. Excuse the introduction promo, but here you'll actually see the motor fire on the pad, or I'm sorry, on the test stand with the system integrated, and we were able to actually get all of the results that we needed to prove to the range that we were actually able to fly this. So the debris that you see flying off is actually water putty. We use that as an ablative to protect some of our electronic systems. When you're actually looking at it, you'll see the vanes move, and you won't necessarily see the entire plume move, but you'll see that the plume will actually start expanding to a certain degree, where you can see that it's actually diverting the thrust. So just kind of a cool slow-mo video. Here you'll be able to see the plume move side to, oh, it doesn't freeze.
It did.
That froze. I have some cooler pictures anyway. But that was the interesting part. We were only vectoring 10% of the thrust, which might be 60 pounds in some case. And we were only actually in the plume, if you look at the actual cross-section of the plume, we were only in about 3%. So it was actually really interesting that we went back and looked at the video that you could actually see the plume respond just a little bit. And you just kind of see the fanning effect. So these two charts, what you're seeing above is the actual commands that we gave the thrust vectoring system. And if you look at the chart below, that's what the thrust stand produced. So you can see the top black chart being the actual axial thrust. The gray that kind of runs the same trend, that's the thrust provided by the vendor. And what you're seeing below, the red and the blue, that is both the pitch couple and the yaw couple for the thrust vectoring. So as you can see, we were actually able to achieve the results that we wanted to. Now, we were only trying to command this was initial testing, so we weren't commanding these to the full 10% capability that we wanted. But this more or less proved that our system actually responds, A, to a trajectory input that we give it, and B, that it actually is able to vector the thrust. So here again, you can kind of see the pitch and yaw couple. You notice they're very similar. We actually exercised the vanes to 5% of their capability, and then back, and then 10% of their capability. So it was really incredible to actually see this work to the way that, for once in our lives, the results are as what we expected, which is pretty cool to see. So here's just some cool pictures that we pulled. You can see some shock diamonds forming both off of the vanes and off of the nozzle. This was obviously the solid that I discussed. Hybrid would look a little bit different. but again, we have interchangeable parts for that. What was incredible about this was the vanes, which were carbon graphite, eroded as we expected, and they actually performed better when they were eroded. So we learned right there that when we have these sharp curves to form the diamond, if we actually round those, we don't get as much shock off of them, and thus we actually get better performance. So we followed up with testing on that, and that proved to be true. And that was the only difference between that test and this test.
How much difference was it?
It was about 7.5%.
Wow.
So
Okay.
it was considerable. It was considerable.
And that was again you rounded the corner, or you rounded what was the rounding?
So if you see our vein shape essentially is a diamond.
Okay.
And as the motor fired for this test, the actual edge here that was in the plume eroded away. So
Okay.
it rounded that corner. And the reason initially that we had that sharp knife edge was just we did compressibility calculations to see where the shock would form, and we wanted them to form after the actual vein. Because if we had formed it within the vein, we would have other effects that would have diminished motor performance. But we found that even after we rounded it, they were still forming after the vein, and you can actually see one of them forming right here. So that result was what we expected it to be. Rounding the veins and increasing the performance that way was not at all what we expected, just based on simple compressibility. So it's very interesting to see that in action. So that rocket that system was designed for, that's actually going to fly this year, and that is aimed for 100,000 feet at this time. It's coming along very, very well. I actually graduated in December, so I passed the torch on, so they better not let me down.
Where are they going to fly that?
They're actually flying it out of Cape Canaveral.
Oh, okay.
Yeah, so
How do you get permission to do that?
But he was talking about that.
So that's why this thrust vectoring system was developed. We had talked with Space Florida. We had discussions with the range, and they were all for it as long as we could produce, a missile system safety pre-flight package, an MSPSP, just as SpaceX would or ULA would, and essentially perform all the necessary, articles and documentation. If we could prove that, they had no problem with us flying. So we developed this thrust vectoring system to put them at ease, to actually allow us to fly. And what was really cool about it is we approached them with the idea of, we understand you're nervous about this, obviously, but we want you to be integrated into our design and testing and show you that the system's working and show you the data and show you what we're doing so that you're also comforted by it. Because when I see documentation and I see a PowerPoint, I don't know how, it can say that's how it was done and I can see the results, but unless I'm there physically seeing it, I don't believe it. That's just how I am. So I wanted to bring them out and show them our testing, show them our thrust stand, and that's what we did, and they were really impressed with it. So it was really cool to interact with them. Now that I worked with SpaceX, they don't even care anymore. So I still get yelled at SpaceX for it. But this flight coming up will be very, very big for the range and for amateur rocketry on the Space Coast, because this opens up a whole new pathway to A, a launch pad, and B, it is capable of having a student project or civilian projects fly out of the range. And they're willing to work with us, willing by definition. But, eventually I see a lot of amateur rockets going out of
huge
there.
launch fee or something?
Nope.
Oh, wow.
Space Florida owns a launch pad, pad 46, I believe. It's either 46 or 36. And that is the pad that we were originally looking to fly out of, but we're exploring other options. The range has really started to open up of using old infrastructure, which is awesome for everybody. And we're trying to bring the amateur side and the low Earth orbit side, to the range now. So hopefully this kind of leads the way with that.
You anticipate that they'd be interested in opening up with some other universities besides that one?
So so we actually...
And because I could think, even as far as, even as far as like up in New York and such, we have universities up there where we're doing it, and we can't get down to the other range because, well, that's all tied up, and then there's other places that they're trying to try these bigger things, and then I'm hearing about this, I've said, well, this should be good, so if you guys can open this up.
And that's where now that I'm not directly associated with Florida Tech now that I've graduated.
Mm-hmm.
I've tried to use other methods, using both my knowledge working at SpaceX and working with the range and working with Space Florida and working with FIT and going through this, to open up a company that could interface this and basically say, you know, we want to work with Space Florida, we want to work with the range to bring projects together. And the whole goal of the Centurion rocket, which I don't have later, but the whole goal of the Centurion rocket was the ability for us to launch to 100,000 to 300,000 feet, to launch CanSats and launch high school projects, whether or not it's, you know, meteorology projects or solar projects, that kind of thing. But at least to give them a vehicle that's capable of what they need. Because that seems to be, at least the issue I've seen on the Space Coast, and I know it's probably all over the nation, you know, groups that get involved with building CanSats, they don't have a way of flying them. So they build a CanSat and it's like, cool.
There's actually only one place that,
Yeah.
And
out of BlackRock when they're flying out there.
And BlackRock's a perfect example. We have several projects, some of the ones named here, that we tried, you know, to bring out the BlackRock.
Yeah,
try to bring out the Nevada, California, and fly. And it's like, we have a range here. Yeah.
Yeah, that's.
And I think it was Quake, the rocket that won the Carmack Prize, flew out of BlackRock. And they're from South Florida. So it's like, why are you going out there? So that's my goal, is to try to open up some kind of organization to start doing this work with. I learned a lot from it, and I would love to do that. And we have flown, like Panther 1. This was a project done years ago. It was a smaller rocket, but that actually flew out of Cape Canaveral Air Force Station. And that was the first time any civilian rocket has been flown out of there. So it's been done before. It's just been abandoned over the last few years until recently. So we're really trying to get that going again. And it would be a great resource not only to fly rockets, but to fly payloads. That's what we're looking at.
yeah, because, you know, we've done, like, you know, smaller altitude launches, and we collected with the college would do it, like, would design the rockets and so forth, and then we collect experiments from high schoolers, even middle schoolers.
Yeah.
And they want to do it, but they're saying, well, we want to get up there. We don't want, we don't want.
Max a mile.
Yeah. Yeah, you know, they don't want, like that, they don't, even higher. They said, geez, we want some serious altitude. And I said, well, we have to have, a range. You got to build the rocket, and we need a lot of those. I said, we could go out west, and maybe do some 30,000 foot launches. And they're going, yeah, okay, but
Yeah. And if
they're saying, but they're wanting to see launches like this, 100, 300,000.
Yeah.
I want to say 100 kilometers.
Did you ever look at wallops?
We did. Again, our argument was,
yeah, it's close.
Politically, our argument was, why are we going to Virginia when we're in Florida?
Right.
Yeah.
And that was actually the argument we brought to the range. And we brought to them a different side of things. We said, ignore technology for a minute. Think of business.
Yeah. I know Florida wants to get more and more out here and streamline, not make it easier, but at least streamline the projects.
Exactly.
Getting signed off.
Exactly.
Where are you recovering down in Cape Canaveral? You about got over the ocean, or?
Yeah.
Yeah, so you have to.
So that is a restriction.
Yeah.
Now we have flown. It's called the Sugarlands down south. It's just on the edge of the Everglades, where we have flown to 85,000 feet and recovered on land. I mean, we're recovering in the Sugarlands, which is a very wet environment, but we had support for that. And unfortunately, that dried up. But that was a great resource.
Yeah, because wilds, you got to recover over the, you got to recover over the ocean too.
Water?
You'd have to recover over water. Now, what's cool about that is we have been told that if you fly out of the range, and if they are interested enough in helping you out, that you would have support from them. And I was told, potentially have a helo operation where you'd be able to find it. And that's actually where our recovery system is based. We have, all the ocean dyes you would need, the strobe, the GPS. And we have the system that we actually developed is almost like an airbag, where as soon as it detects water flow into the body tube, it actually fires a charge and 2 airbags come out. And not only does it seal our electronics bay from the water, it also floats the rocket. It's a little bit more visibility. So that is the drawback. You would have to fly over the ocean, but we did discuss with them if we could control its landing, which we can't, that they would allow us to land it back at the Cape. But that is an environmental
There's that
nightmare.
big space shuttle runway.
Yeah.
You could land almost anything on it. It has
Yeah, you know
little
that.
wings.
Yeah, you could have a glide
Here's
back
something. Here's something that I know a couple of these students were investigating. I told them check it out because the Army had been I don't know, I can't remember if it was the Army or the Air Force. They were experimenting with GPS guided cargo drop chutes.
Yeah.
And we're saying, oh, this is, and they're getting like some unbelievably close. I mean, like they're landing like within 20 feet of their target. I mean, unbelievable for a cargo drop. I mean, usually. And I'm saying, oh, I mean, the devices are kind of bulky now, so I don't know what the.
You should talk to Mark Lupia. He's developing one now for, and he's with Space Support Rocketry.
Mm-hmm. Okay.
What guided? Yeah, because I was thinking
He was playing with his parachute all over today.
Yeah.
But yeah, he expects to make that guided too. It's
Okay.
a triangular.
And that's
But
where
you got the-
that's where we flew out of for a lot of our projects at Spaceport.
And yeah, I know. Equipment manager. I'm the guy that drags everything up for him. Except maybe people's.
Oh, a trailer?
Yeah. I might want to borrow that. Yeah. I know.
So what's SpaceX doing on the 16th? They're gonna try and land vertically on the ocean?
So,
This,
yeah, I got like 2 more slides,
Okay.
and then I'll talk about that. So again, as I covered, student rocket projects at FIT have been around, as you know now, for years, but now we're starting to integrate to where we're launching bigger and bigger stuff. Now that the real kids are gone, I can say this. They're our biggest competitor. We have a love-hate relationship. They're trying to fly to a certain altitude. We try to top them. They try to top us. We try to top them. So it's a fun competition to have because in the last few years, we've seen a lot of awesome rocket projects come out of it. And you need that healthy competition. And it's been cool to see both universities build to that level, have a failure once in a while, learn from it, and kind of come back. So it's been really interesting to see that. So again, been around for years, rocket motor testing, obviously I discussed this. Here's some other pictures where we've used thermal imaging to look at some plume environments.
I always wondered why there was the tripod on the end of the.
Yeah, so that gives us the 6th off capability. Without that, we would have no way to actually measure the pitch and yaw forces.
You know, as soon as you started talking, that's why it's that way.
Yeah. So that's all I have, and I kind of did want to end early on my talk to open up conversation and questions about everything. So I know we kind of went into it a little bit in the middle there, but essentially that's what we have at FIT. The thrust stand being probably our biggest rocket asset right now. Besides some of the high-level research, like we have slosh research with fuel tanks and whatnot. But as far as hardware at Florida Tech that would be of interest, amateur rocketry, thrust stand is pretty cool. We can measure thrust from 0 pounds all the way up to 10,000 pounds with high accuracy piezo's, high frequency collection rates. So it's been a pretty cool ride the last 4 years for me, because I came in not knowing anything about it, and then I took it over and kind of revamped the program a little bit, got started with the Centurion rocket, Vector Bravo, so it's been cool. So hopefully the group that we kind of left it for, hopefully they take control of it and they're able to fly that this year. It'll be really cool. So, yeah.
How long did you say how long did it take overall to make?
So from design to where it's at now, which the rocket was ready to fly months ago, it took about 2 years total. Now, when I say 2 years, that's 2 years of developing the rocket, talking with the range, and developing the Vector Bravo thrust vectoring system. And the Vector Bravo thrust vectoring system, we use that as our senior design project, which has restrictions on it for how fast you can work, and you got to submit a lot more paperwork for it. I mean, you're doing it the right way, but that kind of prolongs what probably would have went a little bit quicker. So it took 2 years. We probably could have had it done in 18 months. But overall, we're looking at a 5-year program from when we test this to 100,000 feet, jump it up to 300,000 feet, and then we have the bigger vehicle. And we're testing motors along the way that have proved successful to get us there. So that's been the incredible part.
It's been interesting.
Yeah.
Going for low Earth orbit
Yeah.
satellite
Yes.
launch? Okay.
And that's where we want to draw the interest of student projects.
I want to put another ham radio satellite up in low Earth orbit.
Well, and where we started getting involved with it was reading on all these projects of students taking CanSats and launching them on weather balloons, which A is boring, and B, you're not getting the actual effect of the flight that you want.
Yes.
We had a group of students who wanted to test slosh in fuel tanks. And with the parabola that we could create with our rocket, we could give them almost 32 seconds of weightlessness. You can't get that with a balloon.
No.
So,
yeah, and like we had a set of students in middle school. They just wanted to test switches.
yeah.
See which ones could withstand, certain thrust. Well, they said, geez, can we get some more thrust here? Because we really want to test these switches to see if they're going to withhold and so forth. Because they figured that was very fundamental. And,
Yeah.
and for middle school, it was a great experiment.
And one of the greatest and simplest tests that I can think of, that proved probably the most beneficial was a student wanted to test batteries sitting on a GPS unit for a model rocket. And at what thrust and orientation do you actually achieve where the spring on the battery is going to
It's
separate?
going to start, because we always worry about that. Yeah, for the little simple one, they always worry about that.
And for a 14-year-old kid in high school, I mean, he had better research than I've seen some graduate students. Like it was pretty unbelievable. And his issue was he couldn't test it. He goes, I have no way of producing, I want to put this on a rocket. I don't want to put it on like a springboard and simulate, the thrust. He goes, I want to put it on a rocket and say, this was meant for a rocket, it flew on a rocket, this is what it did. And that's my mentality on things. Test as you fly, fly as you test.
But you're right where these kids, where these students are talking.
Yeah.
Because like I said, they put together, they put together, like you said, these amateur, well, we call them amateur rockets, but they put together these rockets, like for example, they put together a 3/4 like smoke scale, out of fiberglass. But like I said, even on an end motor roller, which is what they launched, they're only going to go so far, and they're not going to get really want.
That was the neat thing about like that group out of BlackRock recently. They weren't launching those huge motors like everybody else was doing. They did a real nice two-stage minimum to a minimum diameter rocket, and it went to 130K.
See, that's what they're trying. They said that's what they're a lot of these groups they are looking for more minimum diameter stuff.
Yeah.
Problem is they can't do it. There's one high school they want to do gamma rates. I said,
Gamma ring, yeah.
Yeah, they want to set up some. I said, well, we're going to have to get some altitude.
Yeah.
To make.
And what's a shame in it too, and growing up I did all the science fairs and all that as a kid, is if we see it as an educational standpoint, which it should be, is you're not interested in putting your project on a springboard and simulating the force. You want to see the flame, you want to hear it, you want to see the rocket go. And that's how it should be. And that's where I love working at SpaceX, because everyone around me at SpaceX as a kid flew that stuff and wants that. And you might not be following, well, I'm going to say this with a grain of salt, you might not be following the rules all the time, but you're getting to where you want to get, and you're seeing what you want to see, because that's what you want to do. And I feel like that's the mentality that
we
unfortunately...
just call it thinking outside the box.
Thinking outside the box.
Yeah, there you go.
And unfortunately, that's been the mentality that's been lost in the last 10, 20, 30 years. Being able to, take the risk to do something that might fail. But
failure, Edison, how many bulbs, 1,200 bulbs before, something like that, before they got one to work? Oh yeah, you learn a lot with failure.
Well, and what's interesting is at FIT, my background was more propulsion oriented. And I learned more in propulsion when I was helping work our Engine 1 issue on Falcon 9 2 years ago, which was the engine had a failure. I learned more from that than I ever learned putting an engine together and seeing it fire successfully. So that was really interesting.
I remember you being out at launches.
Oh yeah. Oh yeah. So that's my presentation on the FIT part. And if you want to, can you actually turn the camera off for me?
Thank you.